more descriptive than
Yeah.
what's the
But I think
what's the
he's
special
Okay, let's get started. Maybe a few more people will show up. So today we're going to start talking about what Stan is doing, even though we won't actually directly interface with Stan until like April or so. But this is sort of in the meantime we're going to be using Stan without necessarily getting a great appreciation as to what it's doing. So we want to explain that a little bit up front, and then use it without getting too much into the details, and then in April pick it up again with more stuff on the Stan language, which means that it's time to say that I work at Columbia. You go to school at Columbia. Columbia develops Stan with grants and seeking more grants, and the fact that I try to use Stan in the real world creates an appearance of conflict of interest that you should be aware of before learning about what Stan does. And so we want to talk a little bit, pick up where we were on Tuesday, where we were talking about Metropolis, Hastings, Gibbs, and just sort of give a comparison of what I refer to as ancient MCMC samplers, which is pretty much anything before Stan, but Metropolis, Hastings, and Gibbs were being used in the 1990s in social sciences and in physics and image recognition and stuff like that earlier. So Metropolis, Hastings are the special case. Metropolis, which we talked about on Tuesday, it's a very seemingly general approach, because all you have to do is specify the numerator of Bayes' rule and the Q distribution that you want to generate proposals from, and in principle you can draw from this posterior distribution as the number of Markov chain Monte Carlo steps goes to infinity. But in practice you have to choose the tuning parameters, which is kind of difficult to do, and if you do it well, then there's some theoretical results that suggest that about the optimal acceptance rate is only about 23%. And so more than 3/4 of the time, when you make proposals from your Q distribution, your alpha star, which is based on this ratio of the kernel and the PDF of the Q distribution, the alpha star is too low. It's less than a draw from a random uniform distribution. Consequently, you don't accept the proposal. You keep your previous position of the parameters another iteration. And so like only 22% or whatever of your draws are unique. That's what's supposed to happen. But that results in an effective sample size that is at most 22% of what the nominal number of Markov chain Monte Carlo steps you do. And in practice, it can be a lot lower, because even when you do accept a proposal and you do move, you might not move very far in the parameter space. And thus there's a high amount of dependence, a high amount of autocorrelation among adjacent steps in your Markov process. And particularly as you get more than like 1 or 2 parameters, the effective sample size can go to pretty much 0. I put an example on CampusWire after class on Tuesday that did Metropolis sampler based on that ratio of normals PDF that you did on the homework, and it was like terrible for 1,000 steps. It was terrible or pretty terrible for 10,000 steps. It wasn't until I did 100,000 steps of this Metropolis sampler that the CDF of the posterior distribution looked like it was supposed to look, because you can construct it more or less explicitly by doing this ratio of normal. So it took me 100,000 steps to where you could even say it's like doing the right thing. And the effective sample size was 20 on a nominal sample size of 100,000. And so those 100,000 highly dependent draws from that ratio of normals distribution were as good for estimating what the thing is if I'd just taken 20 random draws independent from the numerator and 20 normal draws independent from the denominator and divided those two things. So by doing 100,000, I got the efficiency for estimating this mean of 20, which is terrible. And that is only one parameter, which is sort of the easy case, although it's a ratio distribution, so it has heavy tails. Like that had no chance of turning out real well. But in theory, you can do it. In practice, you never should. And one of the things I don't like about that analogous course at the master's level in the stat department is they spend like months talking about these things rather than like historical stepping stones to where we are now to like actually understanding in detail how they work, even though they don't work well enough for people to be using. We also talked about Gibbs sampling, which is a little bit smarter. So with Metropolis Hastings, you're really just coming up with a guess from your proposal distribution, your Q distribution, and then seeing if you can accept it. Gibbs sampling is a little bit smarter in that it's using the full conditional distributions to make proposals. So the proposals you're getting out are at least tailored to the full conditional distribution, and those jumps are always accepted. So that's a kind of a step in the right direction. But the jumps might not be very big, and that's especially the case if the parameters are highly correlated, in which case the variance of the full conditional distribution is much less than the variance of the marginal distribution because you're conditioning on all the other parameters that are highly correlated with the one that you're updating. And when that happens, the effective sample size can be quite low as well. What the bugs family, so by bugs family, I mean like WinBugs, which is pretty much stalled now. JAGS, which stands for just another Gibbs sampler, which is sort of a more not Windows centric, it works on Mac and Linux version of the same thing. OpenBugs, which was sort of a open source rewrite of the original WinBugs thing, which wasn't really open source. Anyway, all those things, they're Gibbs samplers, and they make it easier on the user, at least seemingly easier on the user, because the user doesn't have to work out what all the full conditional distributions are by, pencil and paper. By now, almost all the ones that can be done have been figured out, but it's still a relatively small set of priors you can combine with likelihoods and all of this in order to get a full conditional distribution that you recognize that has a name that you might have a ready algorithm to draw from that full conditional distribution. When you aren't in that situation, which is really the majority of the time, then you have to fall back to some other method like Metropolis, slice sampling, all kinds of other things that don't work so well in order to get a draw to update that parameter, and then maybe you can do some of the rest of them with draws from their respective full conditional distributions. And so what the bugs family did, and it's actually pretty clever, especially when we're talking about like 1995 and whatnot, of using pattern recognition to recognize, if you simplify this and simplify that, it actually turns out to be a full conditional distribution whose kernel is known. And then it has a bunch of algorithms to draw from a normal, from a gamma, all these things, when it can recognize what the full conditional distribution is. And when it can't, it has some fallback mechanisms. And I basically wrote a R function that only uses one of the fallback mechanisms. And we saw that, it was better than Metropolis Hastings, but worse than Gibbs sampling when we actually utilized the fact that we know the full conditionals of a bivariate normal are themselves normal, which gave us better accuracy, more efficiency, etc. But it still wasn't great. And so all of these things have limitations, although, before there was Stan, Bayesian people were sort of happy to live with these limitations because it was, one of the only ways that could do Bayesian inference, particularly if you weren't, one of those people who could program C++ yourself or something like that. So how does Stan compare to those things? So like Metropolis Hastings, you only have to specify the numerator of Bayes' rule. And so we'll show how we can get around the fact that we can't work out the denominator of Bayes' rule, which in principle is a multidimensional integral. Analytically, we can avoid that fact and still get draws from the posterior distribution implied by our numerator of Bayes' rule, which is to say the kernel of the parameters whose posterior distribution we're trying to draw from. Like Metropolis Hastings, but unlike Gibbs sampling, the proposal updates are joint rather than one parameter at a time. So it's not as susceptible to the problems that Gibbs sampling have, where the full conditional variance gets very small, much smaller than the marginal variance. And so it has a hard time making big steps around the parameter space by not doing full conditional distributions, just proposing all the parameters to be updated at once. You don't fall to that disadvantage. Unlike Metropolis Hastings, but like Gibbs sampling, the proposals are always accepted. So you don't have to pay this, like, I'm only accepting 22% of my proposals penalty in terms of getting what the effective sample size is and things like that. Unlike Metropolis Hastings, but like Gibbs sampling, the person usually doesn't have to tune any tuning parameters to the algorithm. Sometimes you do, and you have the ability to do that, but a lot of times you don't, which avoids a big cost to try to tune a Metropolis Hastings algorithm to get like fairly decent efficiency in terms of effective sample size. Unlike both of those, the effective sample size tends to be quite good, between 25% and 125% of your nominal number of draws. And how can it be greater than 100%? That doesn't make sense. Well, it can be if you remember the formula for the effective sample size. It's the nominal number of draws S plus, or divided by 1 plus 2 times the infinite sum of the kth order autocorrelations. And if you do a Stan model well, the first order autocorrelation can actually be negative. And so some of the later ones, they can be positive, and so there's a little bit of cancellation there. But if the first one is sufficiently negative and the rest of them are not too positive, that infinite sum can actually be negative. And so now you're doing 1 plus 2 times a negative number and dividing by something less than 1. And you can get a nominal sample size that's, or effective sample size greater than nominal sample size, which says it's doing even better at estimating the posterior means than S independent samples would. That's not always the case. So sometimes the infinite sum is a little bit positive, in which case, the effective sample size will be less. But it's usually at least 25% or 10% when things are going well, and that's true even as you get into giant models. So we've seen Stan be done with models that have millions of parameters, and neither Metropolis Hastings nor Gibbs nor anything else scales nearly that well in the size of the model, the number of parameters, and still gives you a decent effective sample size as you run it. So unlike both of those, and this is super important, Stan produces warning messages when things aren't going well. And so it has, because of the way it does MCMC, it has some unique opportunities to tell just from the output that the output is not right. And that's not possible to do nearly as well with Metropolis Hastings or Gibbs. And so when you get warning messages, that's telling you that this posterior distribution is hard for Stan to draw from, and you need to help it out by tweaking some tuning parameters or maybe improving your numerical accuracy, something like that, in order to get it to go up to sort of the usual standards that we have for Stan's MCMC. So all of those are basically all reasons why Stan is pretty much strictly better than both Metropolis Hastings and Gibbs, and like various hybrids of Metropolis Hastings and Gibbs and some other things that I'm not even talking about. But the one sort of advantage for bugs and Gibbs samplers in general, or even Metropolis Hastings, but mostly Gibbs, Stan doesn't permit the unknowns to be discrete. They have to be continuous, and not only continuous, but the posterior kernel needs to be differentiable with respect to all of your parameters. So that's still a huge class of models, but there's some people that say, no, bugs is great because you can have these discrete unknowns, and you can in the bugs language, but it's very hard to sample from a posterior distribution that involves discrete unknowns with enough efficiency to have a good effective sample size. So it's another one of those things. In principle, you can do it. In practice, there's no finite number of draws that you can obtain that's like safe to analyze when you're trying to give sampling with discrete unknowns. So there's ways of getting around that sort of with Stan that we maybe talked about in April. But anyway, for the most part, Stan is better than these things, and that's not really a surprise because all of us who developed Stan had been using Metropolis Hastings and had been using Gibbs sampling, in the early 2000s, and we're familiar with the problems that it sort of caused. And then when we had opportunity to get around those, then that was something that we all spent a lot of effort doing. So what is Stan doing? So before we can really get into Stan, we need to talk about Hamiltonian Monte Carlo, which is another MCMC scheme that was actually proposed also in like the 1990s and talked about, but never really implemented in a serious fashion. But Stan kind of builds on this. So instead of drawing just on the posterior distribution of theta conditional on the data y, Stan is going to augment this posterior distribution or augment the parameter space with the equivalent number of so-called momentum variables that I will denote phi. So the main parameters, like the parameters you're interested in, the location parameters, are denoted theta. There can definitely be more than one of those, but for every one of those, there's this corresponding like shadow parameter in phi, which is known as the momentum. And so now what we're going to try to do is draw from the joint posterior distribution of the phis and the thetas conditional on our data y, x, etc. And it turns out that the best or the easiest prior distribution to use for these momentum parameters is a normal distribution. So we're just going to put a normal prior on those that's independent of theta. And then we have our prior on theta, f of theta in the form of a PDF. And then we have the likelihood function of theta evaluated at our observed data y. So that gives us this sort of joint posterior distribution in principle between phi and theta. And then we're going to integrate phi out of that expanded posterior distribution to just leave us with a posterior distribution of theta given the data. And this works reasonably well, or it's relatively easy because the phi parameters don't go into the likelihood function. So the data contains no information about what these phi parameters are. Consequently, the posterior distribution of the phis is the same as the prior, which is a normal, which is like easy to deal with. So that makes it easier. Moreover, because like conditional on the data, it doesn't have any information about the phis, we can choose the standard deviations of this normal distribution prior on the phis to be whatever we want. And indeed, that is actually tuned by Stan in order to try to give it the best performance. But all of that sort of happens automatically during the so-called burn-in period. So we didn't do this on Tuesday, but it's customary and indeed usually a good idea to let your Markov chains run for some number of iterations and then just throw those away. Don't even look at those. And then after some point in time, start keeping them. That way it has the opportunity to converge to the posterior distribution, and also particularly in the case of Stan, to do its thing where it tries to tune this in order to get you the best possible effective sample size that it can. So the standard deviations of our normal priors on the momentum variables are tuned during the so-called warm-up phase and then we start counting, we start keeping the draws after the warm-up phase is over. But anyway, those, whatever the standard deviations get tuned to be, it's just a normal prior with mean 0 for all these momentum variables. And then the reason why it's called Hamiltonian Monte Carlo is Hamilton was a physicist in like the late 1800s is when he did most of his work, talking about dynamics, how like electrons and particles and stuff like that move through a space. Now, we're physics, we're usually talking about 3 dimensions or 2 dimensions, but the math that Hamilton used to describe how the velocity and the momentum and the location of a particle evolves over time actually applies to infinite dimensional or high dimensional spaces, such as we have here for phi, which, like I said, can be any number of parameters packed into that phi vector. And so then we basically use Hamilton's model of physics to, along with the realization at iteration whatever of these momentum parameters, to move theta through the parameter space. And so we're just going to sort of move the parameters we're interested in through the parameter space using the laws of physics with the side condition that there's no friction and that there's no external forces going on except for this normal momentum realizations from the phi distribution. So this parameter space is going to have, it's going to be like the real number line in k directions. And then there's, one more piece to this, that you have to give a topology to this parameter space. And that topology is going to be defined as the negative of the logarithm of the kernel of the posterior distribution that you want to draw for. So the logarithm of Bayes' rule turns the product into a sum. So that's good for numerical reasons. It also makes it align with what Hamilton already worked out in like the 1800s. The negative thing, it's not like a big deal. It's just you people's experience with gravity is such that down is defined as the direction that gravity is pulling you. And so that is what makes it make more sense in terms of physics. But you don't have to put the negative yourself. You can just define the logarithm of the numerator of Bayes' rule, and it multiplies by -1 internally. So you don't have to worry about that. And then it just uses Hamiltonian physics and the realizations of these normal momentum variables to push theta around in the parameter space. And you can show that this is a valid Markov process. And so the realizations that we would get are draws from our posterior distribution. They're not independent of each other, but the dependence tends to be much less than other ways of doing MCMC. And also, like I said, you can get negative first order autocorrelation, although that requires some amendments that I haven't talked about yet. So that's kind of an overview, but if you're not a physicist, and we actually have a physicist here joining us today who's probably cringing at my explanation of Hamiltonian, but anyway, you don't really need to understand the physics on that deep a level. It's my understanding that if you were like a physics major in college, that this would be like a pretty normal homework-ish problem to figure out, but we're not going to assign you any homework problems that entail you to understand anything about physics, but we will try to show with this demonstration, hopefully, what is going on with this. Okay, so here we have the logarithm of the bivariate normal kernel, except I've multiplied it by -1. So on the, can I get bigger? Awesome. Okay, so no, stop. Okay. On this dimension, I have x, which is one of the parameters I'm trying to draw. On that dimension, I have y, and it's just bivariate normal with means 0 and standard deviations 1, and a positive correlation of 0.75, just like we did on Tuesday. And then the other dimension is the logarithm of the bivariate normal kernel of the PDF. So you can drop the square root of 2 pi business and other stuff like that. But I multiplied it by -1, so it has this like kind of U-shaped thing instead of the way that you would normally see it in 2 dimensions as this kind of hill with like a peak. Now it's been turned over, so it's a trough. So the ones at the bottom are actually ones that have higher density, and the ones over here where it's like 2 on y and -2 on x are very unlikely, which is why they're very high, given that x and y are positively correlated. So it's very unlikely to get 2 on y and -2 on x if these things are going to be positively correlated. And then I have a particle in green here, which is just sitting at some place in the parameter space. And then we're going to hit, so theta, the green particle here stands for theta. So it's at like 0.5, and I can't even tell, but it's sitting somewhere in the parameter space. And then we're going to hit it with random multivariate or random normal in 2 dimensions wind. And then it's going to move around like this. So you can sort of see that it's moving around in a way that is like consistent-ish with physics and the slopes of the thing in 2 dimensions. It's not jumping around or anything like that. It's just sort of going through this space. Yes?
That random wind that you described as Brownian?
Yeah. So independent normals. Anyway, so the wind gives it like a gust of wind, and then it starts moving, but there's no friction. So that's the thing that like seems weird to your eyes. In this basically physics simulation that we're doing, there's no friction, so there's no energy lost. And so unless you like stop it, it will go on forever if you have hit it once with the initial gust of random normal wind. But at some point in time, we stop it just by intervening. And then we can say, well, all the places that it's been since we hit it with the wind, we'll just take one of those with probability proportional to the density, log density that you gave it. And the intuition as to why this works, and then, so that's one draw, and then we hit it with a new realization of random normal wind, and it goes again. We stop at some point, see where it's been, calculate the log density there, and then choose one of the footprints of where it's been with probability proportional to this log density that defines our topology. And with all that, you can show that the resulting draws that you get are a valid Markov process, and the distribution that the draws are converging to is the posterior distribution whose numerator you specified, albeit in log units. Any question?
Is there gravity though?
Yes, there is gravity. That's why it's pulling down.
Right, but
Yeah.
Don't you need wind again, another gust to get it from the bottom?
Yeah, so there's more. You can think about like a big mass here. So it's pulling it down. But what you have to trick yourself into ignoring or recognizing is the lack of friction. So it's harder to go like way up than it is to come down due to the slope of this thing and gravity. But if I hit it with like a hurricane from the like right, it could go like way up this, but with extremely small probability because there's not that much volume out there in a bivariate normal that's positively correlated. But whatever is the probability of like Hurricane Sandy hitting the green thing and knocking it to -2, that is like the posterior probability of that happening under the topology that you specify. Other questions sort of roughly about that? So you can kind of think of us as like we're using the physics as our proposal distribution in a Metropolis Hastings thing. So rather than just saying, okay, we're going to make some updates from like a uniform or whatever, we're going to use this Hamiltonian physics thing to give us a proposal. But it actually works out that our proposals are always accepted. So there's no inefficiency that's being incurred by having to keep the same iteration as in your previous iteration of the Markov chain. And so that makes it like Gibbs. But unlike Gibbs, because of the way this is set up, you can actually get proposals that are far away from wherever you are currently. So, you know, it goes, and then let's say I stop it there. Well, that was pretty far from where I stopped on my previous step of this Markov process. And that can make the dependence pretty negligible or even negative in the first order, which gives us additional effective sample size over the nominal sample size. And when that happens, we say that the Markov process is super efficient. And then you sort of, if your draws are even better than independent draws, you know that this Markov process is giving you efficient results, and then you can calculate your effective sample size. And if that's big enough to give you the accuracy you need, then you can sort of go ahead and confidently analyze those draws. In other situations, the effective sample size is a bit less than the nominal, but it's still pretty good. So unless you get warning messages, you can be pretty confident in these results. And when you do get warning messages, you should not be at all confident in the results. They are wrong. And you should take steps to fix them, but we won't get so much into that until much later in the semester, because most of the things that we're going to do over the next month or so are just going to work perfect like the first time without tweaking anything or anything like that. So that's kind of where we're going to be. Okay, so whoops. So that was Hamiltonian Monte Carlo, but Hamiltonian Monte Carlo didn't really catch on until Stan, because in order to do that, in order to solve the new locations and the new velocities under the laws of Hamiltonian physics, you need to, one, specify the gradient of the log posterior distribution, so the partial derivatives with respect to the parameters, and that's something that is like very tedious and difficult for people to do. And then you have to use those derivatives to solve a system of ordinary differential equations, and we've gotten pretty good at doing that these days, but that wasn't necessarily the case not that many years ago. But anyway, the sort of variant of Hamiltonian Monte Carlo, or what you might call dynamic Hamiltonian Monte Carlo, is called no U-turn sampling, and that is what is implemented in Stan. Actually, the original paper by Matt Hoffman when he was a postdoc here, and Andrew Gelman, isn't the algorithm that Stan is using currently, but it first proposed the no U-turn sampling thing. Now we've had sort of 2 or 3 variations on that. But anyway, so the location of the parameters is pushed around using the normal momentum under Hamiltonian physics. At any instant, you could call it a valid draw from the posterior distribution. But since we don't have friction, the green thing is going to move around indefinitely until we manually stop it. So when do we stop? And what Matt Hoffman proposed when he was a postdoc here was, one of the good things about Hamiltonian physics, it's also reversible. So you can run the green particle like forward in time and backward in time simultaneously, at least in principle. So like where would it have come from if it had been hit with this momentum, etc. So what it proposed was, okay, run the Hamiltonian simulation forward in time, run it backward in time. And so now there's like 2 green particles, or like a green one and a red one or whatever, and let them go. And then when they start to turn around and get, so imagine there's also like a red one here. When they start to turn around and get closer to each other again, then stop. Because the theory behind that is, well, you already sort of ran them outward from where you started. And when they start to turn around and come back toward each other, you've sort of already got a foot map of that thing. And so by stopping it when they start to U-turn and get closer together to each other again, that is what enables Stan to get draws or proposals that are far away from where you started at, and what tends to make the first order autocorrelation negative between adjacent draws, which improves our effective sample size. And so that is sort of, or some variations on that are now what is being implemented in Stan. So what Hamiltonian Monte Carlo traditionally was before Stan, you would sort of run for like 5 seconds and then stop. That was probably less than 5 seconds. Let's say I set it to 3 seconds. You run for 3 seconds, then you stop. And that's sort of your new proposal or whatever. So that's what's known as fixed integration time Hamiltonian Monte Carlo, because one of the tuning parameters, you say like, let it go for 3 seconds and then stop. What Stan or no U-turn sampling is doing, you could think of it as dynamic integration time Hamiltonian Monte Carlo. You're not going for a fixed amount of time. You're going until the thing starts to turn around and the 2 or more really particles start to get closer together again. And then you stop, and wherever you've been, you sort of accept one of those with probability proportional to the kernel of the posterior distribution that you specified with your prior and your likelihood and all that. And so in order to do that, no U-turn sampling has to do a discretization of the Hamiltonian process, which is technically continuous in time, and has to solve a system of ordinary differential equations to do so. And there's like a step size in that solution to the ordinary differential equations that needs to be sort of sufficiently small in order for the discrete approximation to continuous Hamiltonian physics to be accurate enough, and that's also tuned during the warm-up phase. And so oftentimes you don't have to worry about that, but sometimes you do. So you should be aware of its existence. So that is an overview of the algorithm that Stan is using to do Markov chain Monte Carlo, the main one. What we are, with the homeworks and whatnot, have primarily been exposed to is not that algorithm. We haven't even used that algorithm yet. All we've done is the Stan language, or a little bit of the Stan language, how to specify a function in the Stan language. And so when people refer to Stan, there's actually like many different parts to it. So Stan is its own programming language. So that's the part that you've been exposed to the most so far. It includes a translation from that Stan syntax that you've written on the homeworks and whatever to C++. And then you probably saw it took like 30 seconds or whatever for your computer to compile that C++, or maybe less. Anyway, so it's creating this C++ that you don't really have to read. It's there, you could read it, but you don't have to. And it gets compiled into binary code that can be executed really, really fast because it's C++ rather than an interpreted language like R or Python, whatever. It includes new algorithms, most notably no U-turn sampling for drawing from the posterior distribution that is implied by the Stan syntax that you gave it, albeit translated to C++ first. There's a library for both matrix and scalar algebra that hooks into Stan and the algorithms hook into it. We haven't talked about matrix operations really yet. We will after spring break. All we've done is say like fill up a vector, fill up a matrix. We haven't really done like eigenvalues or anything like that, but we will. So what we've used mostly so far is the scalar version or the scalar part of the math library. And anyway, both the matrix and the scalar part support what is known as auto differentiation or automatic differentiation. And this is really one of the main reasons why this Hamiltonian stuff took off once Stan did it, is because you as the user, you don't have to specify any gradients or partial derivatives or whatever. We can teach the C++ compiler how to do the chain rule. And so you might have thought like, oh, the chain rule is really hard or whatever when you learned it the first time. But even a C++ compiler can learn how to do calculus. We have to like program the C++ compiler in order to know how to do calculus, but we can do that with so-called template metaprogramming, which is facilitated by C++. So there's a number of C++ libraries that use this automatic differentiation idea. Basically, in the Stan math library, most every function knows its own derivative, and we can teach the C++ compiler the chain rule so that it can multiply together all these partial derivatives together to get, even in complicated models, to work out the gradient of the log kernel with respect to the parameters whose posterior distribution you're seeking by all those steps in the chain rule multiplied together. And that all happens automatically without the user having to worry about any derivatives. So all you have to do is specify the level of the posterior kernel in log units, and then the differentiation and the gradients and the solving of the ordinary differential equations is all happened automatically. So that is really what made it easy for people to use Stan, whereas it was sort of prohibitively difficult to use Hamiltonian, Monte Carlo, except on simple models before Stan got started about in 2011. So it includes interfaces from R and other software to the Stan language, library, algorithms, etc. We'll only use the R one in this class, but there's also one for Python and Julia and other things. There's R packages that come with Stan programs already written. So we'll start to do that next week, in which case you don't even have to worry about writing things in the Stan language because someone else has already done that for you. All you have to do is specify R syntax that implies what posterior distribution you want, and we can utilize the Stan algorithms in order to get draws from those posterior distributions. We also have packages, not all of which are R specific, that are not all of which are even Stan specific, to help analyze and visualize the draws that we get from a Markov chain Monte Carlo process like Stan. And then finally, there's a lot of people now these days who use it. Like I said, the first day we're over 10,000 downloads from unique IP addresses per day of the RStan interface to Stan. So there's a lot of people who are using it, and they talk on the internet about the problems and solutions that they encounter. And so as we get a little bit farther along, or certainly after this course is over with, there's plenty of opportunity to get help when you need it. So that's sort of an overview of the different components of Stan. And I already sort of talked about auto differentiation, but there's a paper that kind of describes this a little bit more formally, how it is we teach the C++ compiler how to use the chain rule. So how would you use Stan from R? This more or less is like how we're going to use Stan from R in April. But sort of implicitly, these steps are going on, even though you might not see them in the stuff that we're going to do over the next month or 6 weeks or so. So you or somebody else writes a program in the Stan language with a .stan extension that defines the log kernel of the posterior distribution that you want to draw from. And then, so that's not going to happen fully for us until April, but the transpiler of Stan will do two things. It first checks that your program is correct, So you probably saw when you were trying to do this on the homework, you could get all kinds of error messages when you forget a semicolon or something like that, or you say something it's a vector, but it actually evaluates to a scalar, or those sorts of things. But it'll tell you if it's not correct and on what line number that happens, and so you can fix it. And then once you have a syntactically correct Stan program, it will translate that to C++ and write it to the disk so that it can then be compiled in step 2 by your C++ compiler that you had to install. And then that compiled C++ is dynamically loaded into R, where it can then be fired off. So really, 2 and 3 can be done essentially concurrently as far as the user is concerned. And then it runs, and then you get back draws from the posterior distribution, and you can do anything you want with those draws in terms of making predictions, comparing the results to different models, evaluating your utility, taking the expectation of it in order to make a decision, etc. So you'll find that being able to get draws from the posterior distribution, in addition to being necessary, because we almost never can analytically solve the integral and the denominator of Bayes' rule, so we can't get an explicit form of the PDF that's normalized. But it's way more useful to have a bunch of draws from the posterior distribution than it would be to have an explicit form of the posterior PDF that you would just have to do like more integrals on in order to figure out what expectation is. If you have a bunch of draws, then you can just do like mean of those draws, and it's a perfectly good estimate of the posterior expectation that in principle could be calculated analytically, but in practice can't. So it's way more useful to have draws than it would be to have like any other sort of mathematical representation of this posterior distribution. Now, what we're going to do over the next month or 6 weeks sort of hides the first 3 steps. You sort of specify some stuff in R and then out pop the draws, but then we can learn how to do posterior predictive checking and all sorts of other things like that. So here's an example, sort of a preview from April, but for April, but using the bivariate normal example that we did on Tuesday with Metropolis Hastings and with Gibbs sampling. So I specified a Stan file called binormal.stan, which is up on Canvas, but you don't really have to look at it. All it's doing is saying, I want to draw from a parameter space that has 2 dimensions, unrestricted, x and y, and then all I'm doing is calling that bivariate normal LPDF function that we talked about on Tuesday to evaluate the kernel of that distribution in log units. I tell Stan to do that. Refresh equals 0 means don't show me the progress reports. It's virtually instantaneous once it compiles. And then to just print out like a summary, I can just do that. And we can again see that the means are pretty close to 0, which makes sense because this bivariate normal that we were drawing from, I said had a mean of 0 and a standard deviation of 1. So those are all pretty close. You can see quantiles there. And you can see an estimate of the effective sample size, which in this case is a little over 1,100 on a nominal sample size after warm-up of 4,000 draws. So about a 25 or maybe 26, 27% ratio. So that's better than Metropolis Hastings. But this is actually sort of at the low end of what Stan usually achieves. And moreover, the Hamiltonian process that we talked about works really well even in more than 2-dimensional parameter spaces. And that is the reason why it can do that is it's utilizing the information in the gradients in addition to just the information in the levels that Metropolis Hastings and Gibbs and all those sorts of things are doing. They're just using the level of the posterior that you specify, whereas the MCMC process in Stan, it's using the levels, but it's also using the derivative of the function that defines the levels. And that gives it more information to make these really good proposals that can nevertheless be far away from where you were on the previous iteration. So here we get, pretty good, or at least good enough effective sample size But this is just a really simple example. We continue to get really good effective sample size in much more complicated models. And that is what really distinguishes it from Gibbs or Metropolis Hastings. So the fact that its performance is like similar to Gibbs in this case is because this was sort of the easiest case for Gibbs and not one that Stan could, I mean, it does fine, but it doesn't have anything special that it can take advantage of here. But if you try to do this in like a million dimensions, Stan is the only thing that works. And if you try to do it in 5 dimensions, Stan would be the only thing that would, really work well when there's a lot of positive correlation and stuff going on. So that's kind of what it's going to look like. But in the meantime, we're going to be able to utilize the algorithm in Stan based on Stan programs that somebody else wrote. So you just have to sort of specify the R syntax that indicates what posterior distribution you want to draw from, and the Stan program is already written for you. So we won't be seeing this, but this is kind of what's happening behind the scenes. Questions about that? Any of that? Okay, so it didn't happen in this situation. It probably won't happen very much over the next month or 6 weeks or so, but you can get warning messages from Stan that's telling you something has gone wrong. So no U-turn sampling, Hamiltonian in general, only uses first derivatives to sort of do the ordinary differential equation solution, thing like that. So it's sort of a first order approximation to this continuous time Hamiltonian thing. And that's more than fine if the second derivatives are sufficiently constant. Then you just kind of have to take small enough steps, and any function that you want, even if it has like changing second derivatives, if the second derivatives are not changing very rapidly, it still looks linear on small enough steps. So if you take small enough steps, you can do the Hamiltonian thing with enough accuracy. But if the second derivatives are changing very rapidly at some point in the parameter space, and you're only using the information in the first derivatives, then that's when things can get messed up. The solution or the approximation to the continuous time Hamiltonian thing becomes less accurate if the second derivatives are changing too rapidly and your steps are too big. Then you could introduce numerical inaccuracy into the Hamiltonian process, and it results in a so-called divergent transition, which you can sort of imagine from this thing. If it got like going too fast and it wasn't accurate enough, like the green thing just flies off the surface. If you do it exactly, it's always going to stay on there. But if there was like a little bit of miscalculation as to what the gradient really is, because computers are bad at math, then you could imagine it just like flies off the screen. And that is what is known as a divergent transition, when your numerical error accumulates so much that it can't solve the Hamiltonian thing correctly. But we can recognize when that happens with a lot of reliability. And you'll get out a warning message saying that there was like 4 divergent transitions or something like that, which means out of all the different chains and all the nominal number of simulations, on 4 of those, the numerical error got too big and it flew off the surface. And it says, okay, divergent transition, and suggests to increase the parameter adapt delta. Adapt delta is sort of inversely related to the step size that it's using. And it'll say, okay, I was using adapt delta of like 0.9. I suggest you try something a little bit bigger so that the step size is smaller, so that those 4 divergent transitions go away. And it always stays on the surface that you're trying to get draws in the posterior distribution of. Sometimes when you get adapt delta, like there's no value that's big enough, and then you have to think about reparameterizations and stuff like that. But sort of the first thing to try is what it tells you to try, which is sort of make that tuning parameter a little bit bigger, Stan will tend to take smaller steps, and that will increase the accuracy, but it will also increase the amount of time that it takes for Stan to run, because it's got to get from like one side of the parameter space to the other. And if it's taking smaller steps, having to evaluate the gradient and the function that you give it every time, then it has to do more evaluations. And so it takes more clock time to do when it has to use these very conservative step sizes. But that's a trade-off you should be willing to make in order to ensure that this is accurate. If you have divergent transitions, it's saying there's a part of the parameter space that I can't get to with taking this big steps and coming in with this much speed. So I need to slow down in order to not miss part of the parameter space that has positive probability. And if you were to miss a chunk of the parameter space that has positive probability and then take the mean of the draws that you get back, that's a mean not of the whole posterior distribution, but the part of the posterior distribution you didn't skip. And that's the part that you skip is going to tend to be out of the tail. And so skipping that biases your estimate of the true posterior means. And so when you get these warning messages, you need to heed them. But you probably won't see them that much until you start writing your own STEM programs. Another warning that you might see is exceeding the maximum tree depth. So there's a limit to how many steps you can go on one iteration. It's usually 10, but we bump it up in the programs we're going to see over the next couple of weeks to 15. And so you probably won't see this message either. But if you do, it's saying, okay, I was cruising along through the parameter space, and then I hit my step limit, whatever that was, but I hadn't U-turned yet. So I was still going. And then you said I had to stop. And so in that situation, it's saying there's more efficiency to be gained by letting me go more steps. And so if you hit the step limit, then you sort of go from dynamic Hamiltonian Monte Carlo to static Hamiltonian Monte Carlo because you hit the limit. And so raising that limit up would allow it to go farther and actually U-turn, and then you get more efficiency, more effective sample size. And so when that happens, increase the max tree depth, and it will tell you to do that. Another warning you can get is low Bayesian fraction of missing information. We'll probably talk about this more when we see it. But when the tails of the posterior distribution, posterior PDF, are very light, nuts can have some difficulty moving through that efficiently. Nuts is pretty good with posterior PDFs that have heavy tails, even tails that are so long that the expectation doesn't exist. But it's kind of slow in that situation. And so the best is for the tails to be close to Gaussian, but that, can't always be the case. It depends on the posterior, it depends on the data. Anyway, when the tails of the posterior PDF are very light, nuts can have some difficulty, and when it does, it will tell you the Bayesian fraction of missing information is low. In a situation like this, you pretty much only choices are like to run it for a lot more iterations and just wait, or maybe try to reparameterize your model. But there's nothing really with the tuning parameters that you can exactly do to combat low Bayesian fraction of missing information. The final category of warnings that you'll sometimes see is actually just an informational message. It's not a warning, but most people freak out about it anyway. Says like, this parameter should be 0 or should be positive, and I found that it was 0. So like the standard deviation and the normal, if you were estimating that. So by definition, that has to be positive. But like I said, computers are terrible at math. If it gets too close to 0, eventually your computer underflows and just says, like, let's call it 0. But in that case, your normal distribution is singular. It can't have any variance. And so you get back this runtime exception message saying, like, sigma has to be positive, but I found that it was 0. And all that does is basically means like that iteration was terminated short before it reached the U-turn point. But all the other iterations are basically going to be fine. So this is really only happening during the warm-up phase. It's nothing really to worry about. But if you get a lot of these messages after the warm-up phase is over and when the draws actually count, it's basically telling you that your posterior kernel, log kernel that you specified, isn't being able to be evaluated with enough numerical accuracy. And so you might want to double check that you're sort of doing all the calculations as accurate as possible. And we'll see, ways to preserve the accuracy. But really, like the gradients need to be correct to about like 10 decimal places in order for the Hamiltonian thing to not get messed up, which is like way more decimal places of accuracy than you actually need substantively, which is probably like 1 or maybe less. I mean, it depends on your units, but if your units are not crazy, you're usually only interested in like the first decimal point or something like that. But the whole thing needs to really be, the gradients need to be accurate to about 10 decimal places in order for this approximation to continuous time Hamiltonian process to be accurate enough to where it's actually drawing from the posterior distribution that you specify, as opposed to something that's a little bit off from the posterior distribution that you specify. And this will also tend to coincide with warnings about divergent transitions and other stuff like that. So those are some of the warnings. Like I said, I don't think you'll see that many of them over the next 6 weeks, but you might occasionally see one, in which case that's what it's about. And when we get into April, we'll learn about more things that you can do to sort of make sure those warnings don't appear. Questions about that? Okay. Most of the stuff that we talked about this week is not really going to be on like the final. It's just trying to give you information as to what's going on with these Markov processes, and particularly the one with Stan, which is the one that we're going to be using. So just a little bit of information about that. Okay, last 12 minutes or so, I want to talk about the homework that was due today. I didn't remember to knit this, so we'll just have to do it for now off of the R&D file. But okay. So the first question was about these reports that the Intergovernmental Panel on Climate Change puts out, and like the very first statement or paragraph in the summary for policymakers was, we're very medium confident or whatever that the last episode or whatever was the warmest 30-year period in the last 1,400 years in the northern hemisphere. Is that statement Bayesian or frequentist or whatever, and is the evidence for it, the estimates behind it, Bayesian or frequent? So this is definitely a Bayesian statement, which you could see from the footnote about very low, medium confidence, etc., and what's the probability that we think this occurred or will occur when we say something is very likely. Those are all adopting the perspective on probability of degree of belief that something will be true or something was true in the case of the ancient past. And so that is all pretty conventional. But when you get to the estimates, they're like the globally average land and ocean surface temperature is calculated by a linear trend, shows a warming of 0.85 and then bracket 0.65 to 1.06. And so what's the bracket business? Well, there's a footnote that says ranges in square brackets are following the plus or minus are expected to have a 90% likelihood of including the true value that is being estimated. And that is like a giveaway, but it's a very subtle giveaway that this is a frequentist confidence interval. What they're saying is across data sets. So if they had randomly measured the temperature at like different places on the Earth and then estimated the linear warming trend and then calculated the confidence interval and then do that process over and over and over again many times, 90% of those confidence intervals would capture the true warming over the period being studied if you were to be able to even repeat that process over and over again to get independent data sets. So there's nothing subjective at all that can be sort of shown mathematically, but that doesn't tell you anything. Indeed, by the definition of probability from a frequentist perspective, about the probability that 0.65 to 1.06 includes the true amount of warming. Because remember, from a frequentist perspective, probability is sort of a collective property of the independent random realizations that you do. And so to say, like, what's the probability that 0.65 to 1.06 includes the true warming doesn't involve, like, what's the proportion of times that 0.65 to 1.06 includes the true warming. It's either 1 or 0. You just don't know what it is. And so you can't really make probabilistic statements about these sorts of things. You can only say what are the properties of the confidence interval estimator as a whole if you repeated the design over and over and over again, in which case you would get different confidence intervals, but 90% of them would include the true probability. So the estimates that they're using are frequentist, but they're trying to use these frequentist estimates to make or sustain Bayesian conclusions about climate change and things like that. And actually, it doesn't make a lot of sense, but, it's sort of a non sequitur. But anyway, someone realized that there's some like massive slippage here, trying to justify, Bayesian statements about it's very likely that this is the warmest 30-year period or something like that from frequentist estimates. So somebody said, okay, we should put in a footnote so that the 1 in 1,000 people that actually knows what frequentist statistics really entails will be able to see that, oh, this is only expected to have a 90% likelihood of including the thing, not that, we sort of know that it's between 0.65 and 1.06 with probability 0.9. That's not implied by the frequentist approach or the Bayesian approach. And so as far as I know, there's no real usage of actual posterior distribution anywhere that they're referring to when they make reports like this. But there are some people who are actually doing Bayesian stuff with trying to estimate the climate sensitivity and what would be the consequences of it in like 100 years if the Earth were to get re-equilibrated to a temperature that's 2 or 3 degrees higher. So that was mostly the second question was about. So the first part of it, you could just draw a million random normals with mean f and then 0.2 times f is the standard deviation, and then divide it by another independent random normals with mean lambda and standard deviation half a lambda in absolute value, and then you get this prior distribution or realizations in the prior distribution of the equilibrium climate sensitivity that they say makes sense according to physics. Only like 93% of those fall between 0 and 10, which is what they say, or I think they said it after the paper was actually published, what they really consider to be a reasonable range for this equilibrium climate sensitivity parameter. So we want to just keep the ones that fall in that range. And then there's a table in the back where they calculate all these probabilities under the prior that the equilibrium climate sensitivity is like less than 1.5 or greater than 4.5 or whatever. And those can all be calculated just by taking the mean of the draws after you've subset to the 0 to 10 interval. So you can replicate a line in that paper in the table just by doing that. I think the part that most people spend most of their time was trying to write the PDF that goes along with this prior. So if you just sort of think about the numerator and the denominator as separate random variables that are independent of each other, it's rather easy to get draws from this prior. But to work out the PDF of the ratio as a random variable is much more complicated, although it's given on Wikipedia. And here's an example of how you could do that in the Stan language. So let's make that nice and big. It's basically just look at the Wikipedia thing and follow it through, one step at a time. Try to only calculate each thing once rather than having any repetitive calculations. And then it's mostly just a matter of figuring out, okay, what's a vector? What's a scalar? How do we element-wise divide two vectors together? Anyway, you come out, and then this is sort of the final statement in Wikipedia, these 3 lines here, where you combine all the terms together in order to get a PDF. And then you can verify in the next part of the problem that you did it correctly by exposing it to R and then taking the integral of that thing from negative infinity to infinity, because in principle it's defined for that parameter space. And you'll find that that integral is essentially 1 to numerical accuracy when you've done it right. And then in terms of visualizing the black line in the figure on the prior, what you first need to do is integrate it again from 0 to 10, figure out what that constant is. It's about 0.937, or whatever was the proportion of draws that actually fell in that interval when you did it in the first part of the problem. And then that constant you can use when you're making the curve, just divide by the PDF by that constant to scale up the black curve so it matches what was in the paper from the 0 to 7, which contains almost all of the volume there. So you should be able to do that. The likelihood function, also similar, probably a little bit easier than doing the prior PDF in terms of writing this in Stan. You just sort of take a vector and a couple scalars, use the phi standard normal CDF, and you can get out the likelihood, expose that, and then you can recreate figure 2A just by calling the likelihood for E1 and C1, and then looping through 2, 3, 4, or 2 and 3, 4, 5, 6 to make the other curves for the other combinations of E sub j and C sub j evaluated across the range from 0 to 10 or 0 to 7, whatever, of the equilibrium climate sensitivity chi. So that will make what the authors had in figure 2A. Then there's a question like, what's the 4 parts of a generative model in terms of exogenous or endogenous crossed with known and unknowable? So the exogenous knowns are like n, which was 7 or 6 actually, f, lambda, the c values that you're sort of evaluating the hypothesis on, the fact that theta is from 0 to 10. All these things just kind of fall from the sky. We're not questioning anything about them. The unknowable exogenous is chi, the equilibrium climate sensitivity, but it falls in the parameter space that you say. The endogenous unknowns, so they're trying to be explained by this model, are the E's, the evidence for or against or whatever, equilibrium climate sensitivity being like real low or real high. And so that's those sort of combined together to get the likelihood. And then the unknowable endogenous, they didn't sort of explicitly call it this, but they sort of mentioned it in the introduction. One of the things that you could, indeed the reason why you might want to estimate a model like this is that, the cost of a planet re-equilibrating itself to a chi that's like 3 degrees higher, 4 degrees higher, 1.8 degrees higher. What would be the cost of all that in terms of like oceans overrunning cities and stuff like that? It would be probably pretty big if you took the expectation over that posterior PDF. But anyway, you could calculate that given a posterior distribution of chi, the equilibrium climate sensitivity. So in order to get that posterior CDF, you just make a kernel function that evaluates your prior, and then you multiply it by the 6 likelihood contributions. You can do that in loop. Just return it. Then figure out what the constant is when you just go from 0 to 10 rather than negative infinity to infinity. Draw the curve dividing by that constant in order to get the thing to integrate to 1 again. That gives you the blue value. And then you can do the same sort of thing to reproduce the values in the appendix in the table as to what's the posterior probability that this is like less than 1.5, greater than 4.5, etc. It's just integrating from like whatever the lower bound is to whatever the upper bound is, and then remembering to bump it up by the constant of integration that comes out from the fact you're only doing the parameter space from 0 to 10 rather than all the way from negative infinity to positive infinity. So I will knit this, put it up on Canvas. You can take a look at it. Obviously, if you have more questions, be sure to post on Campus Wire. So final thing, I have the readings for you for next week that you can come up here and get. This is from Andrew Gelman's and Jennifer Hill and Aki Vetteri's forthcoming book that talks about the R package we will be starting to use next week. So come up and take a copy of it. As it says on the first page, and the reason why we had to print out things, Andrew doesn't want this to be like spread all over the internet because it would undermine the sales of his book when it finally comes out. So I want to see you posting this on Instagram or whatever it is that you people use these days. But anyway, he gave us permission to print them out for you, but don't be like, making a whole bunch of copies for your friends and stuff. That's it. Oh yeah, that's fine. Thanks.